Welcome to part 3 of the Unit 4 summary review video. Now, Unit 4 is over probability, random variables, and probability distributions. I really hope you watched part 1 over probability and the basic rules. I also hope you watched part 2 over random variables because you are going to need to know all of those skills in order to understand what I'm going to explain to you in this video, which is over the geometric and the binomial distribution. Let's get right into it. First up is the binomial distribution. The binomial distribution is a probability distribution for a very special discrete random variable, meaning that the outcomes are countable numerical values. It represents the random variable x, which equals the number of successes in n repeated trials. In other words, if a random process is repeated where only 2 things can happen on each trial, either success or fail, the binomial distribution counts the number of successes you will have in n opportunities or n trials. Now, what do I mean success? Well, a success is simply what we're looking for. It could be anything, good or bad. It's simply what we're looking to have happen on any specific trial. Now, there are a few ground rules that we have to follow in order for a binomial distribution to work. First, what is success must be clearly defined and the probability of success must be given. We call the probability of success P. Also, the probability of success must stay the same on every single trial or opportunity. It cannot go up or down as the problem progresses. Now, the other thing we automatically know when we have the probability of success is its complement, which would be the probability of failure. So the probability of success is what we're looking to happen, and then failure would be what we don't want to happen, just the opposite of success. Now, the next rule is that every single trial or opportunity must be independent of the next, which means what happens on one trial, whether it's success or fail, cannot affect the next or the next or the next. Now, the last rule is that there must be given a set number of trials or opportunities, which we call n. Now, this is why it actually gets known as the binomial distribution. We all know that the prefix bi means 2. Well, in a binomial problem, you must be given 2 things. A, the probability of success, which we call P, and the second thing you must be given is n, a set number of trials or opportunities. Now remember, a probability distribution must have 2 things. First, a list of all the outcomes, and the second is the probability of each of those outcomes. So since a binomial distribution is a probability distribution, we need to have those 2 things as well. A list of all possibilities for x and the probabilities of each of those values. Okay, so in a generic example where we have 7 trials or 7 opportunities for success, and the probability of success is given to us as 22% on any given trial, then x represents how many successes we could have in those 7 trials. So what are the possible outcomes for the number of successes we could have in 7 trials? Well, we could have 0 successes, 1 success, 2 success, 3, 4, 5, 6, or 7 successes. With only 7 opportunities, we can't have 8, 9, or 10 successes. That's impossible. And you can't have 2.5 successes. You could either have 3 or you could have 2. So that's it for the list of our possible values for x, 0 through 7. Nice and simple. Now, what about the probabilities? Well, here is our generic formula to find the probabilities of each of those individual values that x could take on. Now, all of the pieces of this formula could be explained a lot easier if we use an example. So here it is. Now, David is a member of a frequent flyers club. On any given flight, he has a 22% chance of getting his seat upgraded to first class. In his next 7 flights, how many upgrades can he get? Now, let's start off by checking through all of our rules. First, success is clearly defined as getting an upgrade to first class, and the probability of this happening on any given flight is 22%. Now note, not getting an upgrade is failure. That's the complement. 1 minus 0.22 is 0.78. So we got a 22% chance of successfully getting an upgrade, 78% chance of failing to get an upgrade. Now, we assume, since it's said that there's a 22% chance of getting an upgrade on any given flight, that each flight's chances of an upgrade are independent of all the others. Lastly, a set number of trials or opportunities to get an upgrade is clearly given to us as 7. Now, the list of outcomes is really easy. 0 upgrades, 1, 2, 3, 4, 5, 6, or 7 upgrades. Now, what about find the probabilities? Let's start off with getting exactly 2 upgrades in his next 7 flights. Now, one scenario is he gets the upgrade on his first flight, second flight is a no, third flight's a no, fourth flight's a no, fifth flight is another upgrade, 6 and 7 flights are both no's. Now, this would be success, and then fail, and then fail, and then fail, and then success, and then fail, and then fail. Now, we are allowed to multiply probabilities here because these outcomes are all independent. So that would be 0.22 times 0.22 times 0.78 times 0.78 times 0.78 times 0.78 times 0.78. Now, yes, I'm multiplying a little bit out of order here, but does it matter? Order of multiplication doesn't matter, right? I can also use exponents to make it faster. 0.22 to the second times 0.78 to the fifth. The point is that I have 7 different flights. 2 of them have upgrades, so I have 0.22 to the second, and 5 of them don't. Yes, in this specific situation, I have the upgrade on the first flight and on the 5th flight, but regardless of that, the probability is going to be 0.22 squared for the 2 successes and 0.78 to the 5th. When you actually multiply those probabilities out, order doesn't really matter. But wait, another distinctly different scenario would be no upgrade on the first flight, no upgrade on the second, no upgrade on the third. On the 4th, yes, he gets an upgrade. On the 5th, yes, he gets an upgrade. On the 6th, no, and on the 7th, no. Now, here's the good news. The probability is still 0.22 squared times 0.78 to the 5th. Again, order doesn't matter that we multiply. In that scenario, we have 5 0.78s, not getting an upgrade, and 2 0.22s getting an upgrade. So the real question is, how many ways can we have 2 successes out of 7 trials? Because I just went over 2 different specific scenarios, both ending with 2 upgrades. Now again, the probabilities were exactly the same, but they are different, so I have to take them into account as being different. But how many other scenarios of 2 upgrades out of 7 are there? Well, that is what 7 choose 2 figures out for us. The number of combinations of 2 out of 7 trials. So in our formula to figure out the probability of 2 successes in this problem, the first part, the 7 choose 2, tells us how many different ways we could have 2 successes in 7 trials. Then we have the probability that is the same for every one of those combinations. 0.2 to the square, or 0.22 squared for the 2 successes, times 0.78 to the 5th for the 5 failures. Okay, so how do we calculate the 7 choose 2 to get how many different possibilities we have? Again, we understand that there are multiple possibilities. The probability of each of those probabilities is the same. We have 0.22 squared times 0.78 to the 5th. But how many possibilities are there? All right, there are 3 ways that we could actually figure this out. First, we could use the formula. Now, you'll find this formula in any textbook, you find it on any website, but the formula for n choose x, n trials, we're looking for x successes, is n factorial divided by n minus x factorial times x factorial. Now, for our specific problem, that would be 7 factorial on top, 7 minus 2 would be 5 factorial on the bottom, times 2 factorial. Now, if you do all the math, you get 21. Now, if you're like, what the heck is a factorial? Okay, maybe you don't want to go with option 1, which is using that formula. The second option is you can actually use your calculator. It's really nice and simple. Now, the first thing you have to do is type in 7. Type in 7 first on your calculator. Then hit the math button on the left side, slide over to PRB, which stands for probability. Choose option 3 for NCR. That's exactly what we're doing. N, choose R. Now they use an R instead of an X. Not really sure why. Who cares? So you're going to bring the NCR to your screen and then type in 2. So on your screen it says 7, choose 2. Hit enter and you'll get 21 ways or 21 options. Now there is another way to do it on your calculator, which it actually does all the work for you. And just give me a minute. I'm going to show you how to do that. And that's probably the option you're going to end up going with at the end anyway, because it's kind of a cheat. It actually does all the math for you. But either way, there are 21 different options. So there are 21 different options for having 7 flights and 2 of them giving an upgrade. I already walked you through 2 of them, but there are 19 more. But again, all you need to know is that there's 21 options. For each of those options, the probability is the same, 0.22 squared, 0.78 to the fifth, times it by 21 just to make the math a lot faster. So if you think about it, the formula has three parts. The first part tells you how many ways you could have X successes in N trials. The second part is your total number of successes, and then the last part is your total number of failures. But like I mentioned, on your calculator, we could do it all at once. It could literally do everything. It could do all three parts at once and just jump to an answer without you having to do much work at all. Let me walk you through it. Now, the first thing you're going to do is you're going to hit second, then vars. This is a list of different distributions. You're going to scroll down until you see Binom PDF. That stands for the Binomial Model PDF. Now, when you click on that, you're going to see a menu that asks you for a few things. It's going to ask for the number of trials, which in our case would be 7. The probability of success is next, that's P, 0.22 for our problem, and the value of X that we want to find the probability of, which for our specific problem right now, that is 2. Hit enter, bring it to the home screen, hit enter again, and boom, you get the probability right away, 0.293, which we already knew if we did it the long way, but by using this shortcut in the calculator, we get the answer right away. Now that's it. We can repeat this process for all other outcomes. So to find the probability of 6 or 5 or 3 or 1 success, we could use this shortcut in the calculator. Makes it really easy. Now some outcomes are easier, like 0 successes. There's only one way that you could have 0 successes. That's it. 0 successes, all 7 failures. 0.78 to the 7. The 7 choose 0 is just 1, and try it on your own if you want, but it's just showing you there's only one way you could have no successes, all failures. That's it, one way. And then 0.22 to the 0, anything raised to 0, no successes. Successes 0.22, raise it to the 0 because there's none of them. Well, anything raised to 0 is going to get you 1. So at the end of the day, that probability is pretty easy, 0.78 to the 7th. Now the same thing can be said for 7 upgrades. One way you could have 7 upgrades, they're all upgraded, 0.22 to the 7th. 7 choose 7 is 1. There's only one way it can happen. And then for the 0.78, well, you raise it to the 0 because there are no failures since they're all successes. And anything raised to 0 is 1. So at the end of the day, we would just get 0.22 raised to the 7th. But no matter what, the shortcut on the calculator gets you the answer every single time. So here is the final probability distribution showing all outcomes and their probabilities for X. How many upgrades David can get out of 7 flights. Now you may have noticed on your calculator underneath the binomial PDF is a binomial CDF. What is that? Well, let's try it out. All right, so the first thing we're going to do is we're going to hit second vars and then we're going to scroll down until we find the binomial CDF. Now the screen looks exactly the same other than it does say binom CDF at the top. It's very small, but big difference in what it does. Now it's going to ask you for the number of trials, which we're going to put in 7. It's going to ask you for the probability of success, we're going to put in 0.22, and it's going to ask you again for X. But when using the CDF, it will calculate the probability of the outcome you put in for X and add to it all outcomes less than X. So if I put a 4 there, it will find the probability of 4 successes, but it will also add in 3, 2, 1, or 0 successes. So it's going to accumulate the number you type in and anything below it. Now this can be very, very handy if you were asked to find the probability of at most 4 upgrades. It's going to save you time because at most 4 upgrades means 4 or less. So rather than doing 4, then doing 3, then doing 2, then doing 1, then doing 0, and adding them all together, you could just do a binomial CDF, typing in a 4, and it's going to calculate 4, 3, 2, 1, and 0 all for you. Let's do one more example here that you might actually see on an AP exam or maybe a multiple choice question on the AP exam. What is the probability of 4 or more upgrades? Okay, let's walk through first off what that represents. 4 or more. That would be 4 or 5 or 6 or 7 upgrades out of the next 7 flights. Now, one way we could do that is to actually take the time to calculate the probability for 4, 5, 6, and 7, add them all together. We could either find those probabilities the long way, doing the work by hand, or we could use the PDFs, a PDF for 4, a PDF for 5, a PDF for 6, a PDF for 7, get those probabilities and add them all together. But another thing we could do is think about the complement. What do we not want? The opposite of 4 or more is 3 or less, 3, 2, 1, and 0. And that's exactly what a binom CDF could do. It could do the number less. So if I do a binomial CDF, 7 trials, probability of success 0.22, and I put a 3 for X, because I'm doing a binomial CDF, it's going to automatically calculate 3, 2, 1, and 0. Now remember, that's what I don't want. I wanted 4 or more, but if I find what I don't want, I could do 1 minus that, and I could always get what I do want. So in order for me to find this probability very quickly, all I got to do is a binomial CDF with a 3. That's going to give me the probability of 3, 2, 1, and 0, which is 0.954. Then I just got to do 1 minus 0.954 to get 0.046. So the probability of getting 4 or more upgrades of the next 7 flights is about 4.6%, 0.046. So again, you have 2 different ways to do it. You could take the time to calculate what it's asking for, 4, 5, 6, 7, or you could do the binomial CDF to do everything else, 1 minus it to get your answer a lot faster. So if you know how the binomial PDF and the binomial CDF work, it should make finding any probability with a binomial distribution really, really easy. Now, some kids could say, well, if the shortcuts are on your calculator, why would I ever need that formula for the binomial distribution and its probabilities? Well, I mean, you're right, to be honest, but one thing I could definitely tell you is that there could be, or there will be, a multiple choice question where the choices are not to find the actual numerical answer to the probability, but to choose the proper formula that would find you the answer. So they're going to make sure that you know to recognize what that N choose X represents and what the P raise the X represents and all those different, like I said, 3 parts that probability formula. So I know that the calculator could do a lot of the work for you, and that's awesome. It's going to save you a lot of time, but you have to know how to show your work, whether it be for a multiple choice question that's going to show your work or for an FRQ where you kind of have to show your work. Now, like all discrete random variables, we could calculate the mean and standard deviation of the random variable using the formulas that I taught you in the part 2 video over random variables. But if you have a binomial situation, a binomial scenario, we actually have 2 amazing shortcuts to find the mean and standard deviation for you a lot faster than what those formulas are going to do for you. Here is the formula for the mean. All you have to do to find the mean of a binomial distribution is take n times p. It's that simple. It's one of the easiest formulas in the world. To find the standard deviation for a binomial distribution, you have to take the square root of n times p times 1 minus p, which is the complement. Now, in our scenario, the mean is going to be 7 times 0.22, which is 1.54. And the standard deviation is going to be the square root of 7 times 0.22 times 0.78, which is 1.096. Now, these 2 formulas for the mean and standard deviation of a binomial distribution are given to you on the AP exam. But what matters most is that you know how to explain them. So in our scenario, this would mean that in the long run, after many repetitions of this scenario with 7 flights and looking for upgrades, we expect to see an average or a mean of 1.54 upgrades out of 7. But of course that number could vary, it could be more, it could be less. That's where the standard deviation of 1.096 comes into play. Now let's tackle the geometric distribution. It too is a discrete random variable where its outcomes are countable numerical values. In the geometric distribution, we let the random variable x be the number of the trial on which the first success occurs. So we still have a couple ground rules. All right, first, we must have success clearly defined, and the probability of success is given to us, and the probability of success stays the same from trial to trial. Now, anytime you know the probability of success, you automatically know the complement, which is the probability of failure. We also must know that the trials are independent, which means what happens on one trial, success or fail, cannot impact the next. But there is no n, there is no set number of trials, because all we care about in the geometric distribution is when we get our first success. As soon as that first success happens, we are done. The distribution ends. We just want to know when that first success occurs. Now let's use the same scenario we used earlier. David's chances of getting an upgrade on any given flight is 22%. Let x be how many flights he takes until he gets his first upgrade. Okay, first off, we have to list the possible outcomes. So he could get his first upgrade on the first flight, 1. He could get his first upgrade on the second flight, 2. On the third flight, 3. On the fourth flight, on the 6th, on the 7th, on the 8th, on the 9th, ... Oh boy, Countable, yes, but technically infinite because he could get his first upgrade on the 100th flight. That would be 99 straight failures, and then on the 100th flight, he gets his first upgrade. So this is discrete because they are countable, but technically they're never ending. Now let's move on to calculating the probabilities of these scenarios. I think you're going to find it a lot easier than the binomial distribution. Here is the formula to find the probability of getting your first upgrade on the X trial. All right, let me explain how this formula is going to work. Find the probability that his first success happens on the 5th flight. This would be a failure, no upgrade, and then another failure, and then another failure, and then another failure, and then on the 5th success, he gets his first upgrade. So again, we are allowed to multiply here because the outcomes are independent. So that'd be 0.78 for the first failure, 0.78, 0.78, 0.78, and then on that 5th trial, 0.22 for the success. So I could shorten that up with exponents, 0.78 to the 4th times 0.22, or 0.0814. Now there's only one way this can happen. That's it. If he wants his first success to be on the 5th flight, there's no combinations. There's no, well, it could happen this way or it could happen that way. No, there's only one way it can happen. Fail, 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 success. Now here is the probability distribution for X, or at least the start of it. But what we do see here is that as the value of X, the trial of the first upgrade, gets higher and higher and higher, it becomes less and 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 less likely, to a point where it still is not zero. It'll never ever be zero, but it basically becomes impossible. Now, a great AP question for a geometric model might be something like this. What is the probability he gets his first upgrade after the 3rd flight? This means it happens on the 4th, or the 5th, or the 6th, or the 7th, or the 8th, dot, 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 dot. It just says it happens after the 3rd. I don't know when his first success is. It just happens after the 3rd. How am I going to figure this out? It sounds kind of impossible. Well, no, actually not. It's very easy to do. In fact, we actually have 2 ways that we could solve this. One way is pretty easy, and one way is really hard. Let's start off with the hard way so you appreciate the easy way. Now, the hard way would be to think about the complement. We do not want the first upgrade on the 3rd flight, the 2nd flight, or the 1st flight. So we can find these and add them together. Then since we want the complement of that, we don't want it to happen on the 3rd, 2nd, or 1st. So if we find that probability, we could then do 1 minus it, and we'll be left with 4th, or 5th, or 6th, or 7th, or 8th, or 9th, or dot, 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 dot. So the probability that his first success is on the 3rd flight would be 0.78 squared times 0.22. 2 failures followed by success. Or on his 2nd flight, that would be 1 failure, then his success. Or it happens on his very first flight, that'd be just 0.22. We're done. No failures at all. It happened on his first flight. So multiply and add those together, we get 0.525. Again, that's the probability that his first success, his first upgrade, is on the 3rd, the 2nd, or the 1st. Now that's what we don't want. We want literally everything other than that. So we do 1 minus that probability to get 0.475. Now that's the hard way. The easier way is to just think what we want here. We want the first upgrade after the 3rd flight. When do we get the success? Well, I don't really care, but we do know this. The first 3 flights have to be failures. Then, when does that first success come? Well, I don't really care as long as it's after the 3rd flight. But again, if I want the first upgrade to happen after the 3rd flight, all that has to happen is that the first is a failure, 0.78, the 2nd is a failure, 0.78, and then the 3rd is a failure, 0.78. So 0.78 raised to the 3rd is going to get me right to my answer of 0.475 right away. That's it. Now, once again, being a discrete random variable, we can calculate the mean and standard deviation of a geometric distribution. We could use those ugly formulas that I taught you back in part 2 of our random variables, or just like for the binomial, we have some special formulas for the geometric distribution as well. To find the mean of a geometric distribution, all we have to do is do 1 divided by p. To find the standard deviation of a geometric distribution, we take the square root of 1 minus p divided by p. Those are the formulas that they're giving to you on the AP Stats formula sheet. Now, in our specific scenario, the mean would be 1 divided by 0.22, or 4.555. The standard deviation would be the square root of 0.78 divided by 0.22, and we get 4.014. Those formulas are pretty easy to use, but it's way more important that you understand what they represent. So in the long run, we would expect a mean of 4.55 flights until we get our first upgrade. But it could happen sooner or it could happen later, so that's why we have a standard deviation of 4.014 flights. Well, that's it for the binomial and geometric distributions. If you understand the formulas to find their probabilities and you understand the specific situations where they occur, it's actually, well, I hate to say it, but not too bad. All right, hopefully you learned a lot through these 3 Unit 4 summary review videos over basic probability, random variables, and this one, the binomial and geometric distributions. Put them all together and you just reviewed all of Unit 4. It is a lot, but let me say this one more time. I said this in the very, very beginning of Part 1. Unit 4 is one of the hardest units. Ask your AP Stats teacher. In fact, ask any AP Stats teacher across the country. I guarantee you they will tell you that Unit 4 is where most students struggle. So I wanted to make these videos long so I could take my time to explain everything to you and I could get all of the information in. Hopefully you enjoyed them, hopefully you learned from them, and hopefully you keep watching my videos and sign up for the Ultimate Review Packet.